Now we're ready to talk about the first few network metrics, but before we do, I wanted to just emphasize a few things about visualizations. Edward Tufte, who wrote a series of books on effective data visualization, said, "The success of a visualization is based on deep knowledge and care about the substance and the quality, relevance, and integrity of the content." In other words, you should know your network. You should know what you're visualizing in order to visualize it most effectively. Here are his 5 principles in the theory of graphic display. Above all else, show the data, maximize the data ink ratio within reason, erase non-data ink within reason, erase redundant data ink, and revise and edit. Now, this is a little bit different when we're talking about network visualizations. They're actually notoriously hard to interpret, and so we don't really have the luxury of very clear plots where we're deciding that we don't want this shading or that. But what we can take from this is that we don't necessarily want, 3D spinning visualizations, because all that's going to happen is we're going to see some balls with sticks sticking out of them that are flying around in space, and no one is going to get anything out of that. We should try and see what it is what is interesting in the data. Perhaps it's the geographical location of the nodes. Perhaps it's different communities. Can you bring out the communities with the visualization? Or maybe there's some especially significant nodes because of their position in the network. Can you highlight those nodes in some way? So that is basically what we are going to be after. Also, there are things that you want the automated network layer algorithms to do. The first I mentioned when we were talking about the Girls Dining Table Partners network, which was that you want to minimize edge crossing. So here is the same network visualized in 2 different ways, and this is better because it's minimizing edge crossings. Here you have an edge crossing, and so it looks a little bit less clear that this node actually doesn't have anything to do directly with these, that it's actually closer to this particular node, the one that it's linked to. Another thing that you'd like to have are uniform edge lengths. And here you just like the nodes that are connected to be about the same distance from each other. And this is better, for example, than this visualization where we may not know that this node is connected to these others, and here we may not even really see the edge between these two. Now there's an exception, which is when you have weighted networks, and that happens, for example, here you may want this node to be far away because actually these edge weights, which we'll talk about in just a sec, are fairly low. So you want to represent that distance between the nodes, and perhaps these two that are directly connected are very closely spaced. Maybe they're very tight. Maybe that bond is very strong, and so you do want them to be closer together. So it depends. Again, you want the network to effectively represent the data. Finally, one thing that I was doing was I was moving nodes away from edges that weren't incident on them. So here, for example, we might be confused thinking that this one node might be connected, have an edge to this node and another edge to this other node, but in fact, it doesn't have an edge to either of them. It was simply overlapping with that edge. So that is something that we like to avoid as well. And your ability to avoid such problems, of course, depends on the size and the density of the network. The smaller and the sparser the network, the more successfully layout algorithms can satisfy these conditions simultaneously for all nodes and edges. Now let's get to the metrics that we were going to discuss. We have the degree and the degree distribution, and then connected components. The degree is just going to tell us how many edges are incident on a node. So for example, we were talking about the girl Eva and how many other girls had named her or she had named. Now already you see that there is this property, directionality of the edge. And if an edge is directed, you can also call it an arc or a link. So for example, the relationship might be A likes B, A gave a gift to B, A is B's child. You can also have undirected edges. For example, A and B like each other. Of course, these relationships aren't always symmetric, as we saw in the dining table partners network and actually in many social networks, but sometimes the feelings are mutual, and so it can be treated as undirected. You can have A and B who are siblings, or A and B who have co-authored papers, for example. There are other kinds of edge attributes aside from the direction. So one of them is weight. For example, if you have the number of messages sent between two individuals, that could be the weight of that edge. And it makes sense, the more messages that two individuals send, the higher the weight you put on that edge. And of course, you can scale it differently. It could be linear or log weight. And depending on what your goal is, you're going to choose different and appropriate weights. You may also have ranking, just as we saw, the first and second choice of dining partner, but also maybe you're rating your friend from closest to least close. You may also have different types of edges. So some of your social ties are friends, some are coworkers, some are family. And finally, there may be properties that you're assigning to the edge that really depend on the rest of the network. And this we'll get into later, but some edges might be between, kind of acting as a bridge between two different areas of the network. And so they might have a special role, or what's called, the properties called betweenness. So we'll be calculating such properties, and edges, of course, can have any sort of property that you calculate on the graph. Going back to our schoolgirls and their choices, we see both that the edges are directed and that they have this ranking, the first and second choice. Of course, there may be a multitude of other things that you could add on there. For example, maybe some of the girls share a dorm room, etc. But in this data, we're just looking at first and second choices and the direction. The edge weights that you add can also be positive and negative weight. For example, a person trusting or distrusting another. Here I'm showing a fraction of the ePinions graph. Now this is a publicly available data set that we will be actually working with. And what it is ePinions is a website where users go and they rate products. Now product ratings they depend on the individual who's giving the rating, and not everyone's opinion might be your own. So you have the option of saying whether you trust or distrust a particular individual, and this then influences whose ratings you're going to be shown and which products you are recommended. Now in this fragment, you can see that there's a negative community here of lots of people distrusting one another that's tied to a community that primarily trusts. And there are very interesting research questions around this. For example, if you look at sets of 3 people, is it true that an enemy of an enemy is my friend or not? How does this play out in the data? How is this data represented internally? For example, if you're writing code or if you're just using some software, how is the software representing the network? The most basic way is with an adjacency matrix, but we'll also talk about edge lists and adjacency lists. Here is a very simple network of 5 nodes, and here is its adjacency matrix representation. And for example, if we look at node 1 is represented by this row and actually has no outgoing edges. However, it does have one incoming edge here from node 5. So let's see how this works. The entry in the matrix is 1 if node I has a directed edge to node j, and it's 0 otherwise if I and j don't share an edge. Usually, the diagonal of the matrix right here is 0 because usually you don't have self loops. However, in some cases, you can have self loops. For example, if the network represents who nominated whom for a certain office, well, individuals can nominate themselves, and you may very well want to have self loops represented. And in general, you don't necessarily have that Aij, that entry, is equal to Aji. This would happen if the network is undirected. Well, it would be true in all cases if the network is undirected. That is, I linking to J always means that J links to I. Of course, in a directed network, you can have lots of instances of the edge being reciprocated. For example, when you look at friendship networks, a lot of friendships will tend to be reciprocated. We don't have to always use the full adjacency matrix. We can also use the edge list, and it's just a bit shorter. So you can have, instead of a bunch of zeros, you just list the things that are there. So 2 has an edge to 3, 2 has an edge to 4, etc. Now you can become even more compact than that. Especially you may want to do this if the network is very large and very sparse. Sparse means that out of all the possible people I could be friends with in this world, the billions of people, maybe I'm only friends with a few hundred. And so instead of having a billion zeros, I may want to just have an entry that says Lotta, and then it lists, first friend, second friend, third friend, etc. It's much more compact. So going back to our network of 5 nodes, we have an empty adjacency list for 1. For 2, we have that it has edges to 3 and 4, etc. Now, after we have done all of this nice representing, we can start to calculate degree. And degree just counts the number of incident edges on a node, and we may be interested in such things as who is the most popular. Can we count how many edges each node has and which one has the most edges? So again, it might matter whether your network is directed or not. Imagine that you have a network of who has loaned money to whom. If it's a loan network, then the in degree might represent how many different people did you loan money from. Out degree, on the other hand, might represent how many people did you lend money to. And so in that case, owing a lot of money, having high in degree may be less desirable than having high out degree, having people owe you. In other networks, you may not care about the directionality. So for example, if it's a friendship network and people are simply saying who their friends are, you may just want to treat the network as undirected and just count the degree. Or if you have a network of co-authors, again, you might just look at how many co-authors has a particular researcher had over the span of the last decade, for example. Now, you may be thinking, well, it's not all about how many friends you have or how popular you are. There could be more important things, namely having to do with who your friends are. Maybe having a few quality friends or having a few well-connected friends might be more useful in some sense than having lots and lots of friends who are otherwise hermits. They don't interact with anyone else. So in week 3, we will consider other measures of centrality. But for now, we're just going to treat centrality, this importance of nodes, simply based on the immediate network neighborhood. So your direct neighbors in the network as opposed to the whole network. We can calculate these values from the adjacency matrix. For out degree, we're just summing the non-zero entries in a given row. So here, the third row tells us that node number 3 has 2 outgoing edges. So its out degree is 2. On the other hand, from the column, by summing the non-zero entries, we find that 3 has 1 incoming edge, and that is from node number 2. So its in degree is 2. Now, once we've calculated the degree of each node, whether it's in degree, out degree, or undirected degree, we can start to construct the degree sequence. and that is actually just the array that contains the degrees of each node. The degree sequence, in turn, can be folded into a degree distribution, where, for example, for this network, we can count one node that has 0 in degree. We have 4 nodes that have in degree 1, and 3 nodes that have in degree 2. And so then this is the distribution of degrees in the network. That is, it's fairly evenly distributed between the nodes. The next question we can ask is whether everything's connected. So here is a visualization of my Facebook network, and as you can see, there are several disconnected components. This can be quite significant. For example, if there is some vital information in one part of the network, if none of those individuals are talking to the rest of my network, of course they're linked through me, but let's imagine that I'm out of the picture, so it's just all my friends are on their own, they have to communicate, that there would be no way for that information to spread from that isolated component to the rest of the network. It may not be information, it could be a virus that's spreading some sort of disease, in which case you may very well want to be in one of these small components, because it means that whatever is spreading in here, you're actually safe from it, because you don't have any contact with anyone in the rest of the network. And so the overall connectivity of the network is actually fairly crucial. We want to know, is everyone reachable from everyone else for the most part, or is the network so sparse that most people have no way of contacting each other through intermediaries? Again, we're going to pay attention to whether the edges are directed or not. And if you do pay attention to that, you can calculate the strongly connected components. The strongly connected components are ones such that you can reach any node from any other node in the network by following directed ties. So for example, here with B, C, D, and E, you can start with any one of them and actually kind of move around here, right? So you can reach any one from any other one. However, A is in a component off by itself, because even though you can reach A, say you start at C, you can go to D, you can go to E, you can go to A, but once you're at A, you can't go back. And the condition for the strongly connected component is that you can really go from any node to any other node within the strongly connected component. And here's another component that's completely disconnected. Here, G and H are in the same strongly connected component, but again, even though from F you can reach G and H, you can't get back to F. So F is its own one node strongly connected component, while G and H are another strongly connected component. When you have an undirected network, or you choose to treat your directed network as undirected, then you can calculate the weakly connected components. And here now, because we're allowing this edge from E to A to be undirected, that means you can go from E to A, but you can also go from A to E. And now A, B, C, D, E are all in the same strongly connected component. And similarly, F, H, and G are in the weakly connected component, right? So this is a weakly connected component, and this is a weakly connected component. And if you're dealing with an undirected network, you can simply just say connected component. You don't always have to say weakly connected component. But if it's directed, you want to make the distinction. There is also the notion of a giant component, and it is the largest component, and if it encompasses a significant portion of the graph, it can be called a giant component. Now, this significant portion of the graph doesn't actually have to be the majority. Technically, the definition is that as the network gets infinitely large, the giant component is still going to occupy a finite fraction of it. So that's the technical definition, and practically speaking, if you observe pretty consistently under different conditions that your network has a largish component that occupies most of the network, then you can call it the giant component. And here's the giant component in this particular network. So just to recap, what we showed in this mini lecture is that networks can be represented as matrices, or adjacency lists, or edge lists. And we talked about useful network metrics that we're going to start out with. This is the degrees of the individual nodes and the degree distribution of the network overall. And then we talked about connected components, strongly connected components and weakly connected components in directed graphs where strongly connected components obey the directionality of the edge, and then the giant component, which arises in many networks and is the largest component in a graph that is not too sparse. And we'll talk about the giant component more when we talk about random graphs.